All right, for those of you in the room and coming in, our next presenter is going to be one of our online presenters. If you have questions in the room that you want to pause and ask him, sort of wave at me, and I have a microphone that I can use to let Steve know that that we have questions on this end. I'm told that this middle microphone here is actually live and goes directly to the Zoom rooms, so that if you speak up and speak loudly when you ask your question, it should be able to be picked up by the mic, and then I won't have to do all the repetition. And it'll keep things going a little more smoothly and quickly. And I think that was all the technical stuff. And then we'll hopefully have just a short leg stretch break in the middle at about 11:15. And then this will run up close to 12 when we have the lunch break until 1:30. Are there any organizational questions anyone in the room needs to ask? Any clarifying stuff online that we need to get out of the way?
Just to remind people to, if they have any online questions, to put on the chat so we can read them.
Okay. All right, so we're all set to go. And so Steve, if you'll take it away.
Okay, thanks, Brett. Okay, I'm Stephen Phillips. I'm going to take the next two sessions, sort of give you a introduction to category theory from two perspectives. One is treat category theory as kind of a way of doing analogies, and from another perspective, this notion of compositionality, both from a geometrical perspective and an algebraic perspective. And someone asked, I think at the beginning of the session today, you need to know much mathematics. Well, for this talk, I'll try and make it as intuitive as possible and minimize the mathematics. But at some point, we'll introduce a little bit of maths as well. So the first session will just be parts 1 and 2, an introduction to what I'm going to talk about, basically. The what, why, and how of category theory from the perspective of thinking about categories in terms of analogies. There are many ways of introducing category theory, but I think this is probably sort of a reasonably intuitive way for cognitive scientists, given that analogy theory is a large and important part of cognitive science. And then we're going to start off with this notion of compositionality, an important concept that's both in category theory and cognitive science. And then in the second half, so the first part will just be very intuitive. And then the second part will start to make these correspondences and introduce these three basic concepts that Brett had already introduced, categories, functors, and natural transformations. But because we're doing this for cognitive science, we're going to do this, align these concepts with some notion of compositionality, some notion of representation, and some notion of re-representation or computation. And then the second half, the second session, then we'll move on to this notion of universal construction. Okay, so when someone asks, when you say you're doing using category theory, the first question most people ask is, what is category theory? And there are many ways to introduce category theory, and the three ways that are closely related, which I'm going to use today, is category theory is a theory of structure. When I introduced myself at the beginning of today's tutorial, that's sort of one of the motivating points for me to get interested in category theory. Everyone talks about structure, but often in different and crucially different ways. And then category theory is sort of a way to think about, sort of a general way of thinking about structure. And there are many concepts in category theory, and even if you don't use category theory directly, there's some notions of structure that you probably wouldn't be aware of otherwise. At least I wasn't when I started. Then I introduced category theory as a kind of way of doing analogy, and then this notion of universal mapping properties. That's the what of category theory. And then why is it important? Well, we already discussed that in our introduction as one reason as a kind of lingua franca for cognitive science. There are many models. It's often hard, and the models are becoming increasingly complex. And it's often hard to relate models to models. And one way of doing that is to see its sort of categorical structure as a kind of landmark to sort of orient yourself to various notions of structure that models try to capture. Another interesting, and the main point I'm trying to get to at the second part of this talk is the notion of universal mapping property as a sort of principle for cognitive science. And what that means, I'll explain as we get to it. Okay, so let's look at category theory as a way of thinking about analogies. Okay, so conceptual analogy, like that you're familiar with, is something like pen is to paper as chisel is to stone. And so we can think one way of thinking about category theory, analogously, category theory is to mathematics as analogy theory is to cognitive science. So compare, for example, David Gartner's famous structure mapping theory as a map between some sort of source information. So for example, here we have the idea of conceptual analogies. The relationship between pen and paper is similar to the relationship between chisel and stone. And in an analogy, we map elements in the source to elements in the target. So here is the source on the left-hand side and set the target on the right-hand side, such that there is some sort of corresponding relationship between those relations. So it's a kind of a second-order relation, or a relationship between relations. This is quite similar or analogous to a very basic concept in category theory. That's the concept of natural transformation, shown down in the square here. It involves several things, but as you can see, quite straightforwardly, quite plainly, that it's somewhat similar in the sense that there is a mapping between these elements on the left-hand side, these objects in arrows, these two objects in this arrow, to some corresponding objects and arrows on the right-hand side. And we're going to use this as a kind of central concept throughout this. I'm going to use this as sort of a central, sort of a unifying concept throughout this talk. Okay. Okay, so the starting point for our introduction to category theory is this notion of compositionality. Compositionality, we're going to think of category theory as a formal framework for thinking about compositionality. For example, suppose you have this expression, John loves Mary, on the left-hand side, and it maps to some sort of conceptual representation of John loves Mary on the right-hand side via this mapping here. So and this is sort of a basic notion or a classical notion of compositionality in cognitive science. But in category theory, we're going to look at this as sort of the unifying idea in two ways, both as in sort of a geometric way, this square of relationships as a kind of geometry to it. And also, it's not just any square of relations, there's an underlying algebra or typed square that's important too. And both these aspects and how they relate to each other are important to getting an understanding of category theory and what's going on. Okay, so here's a sort of a table of corresponding concepts. So I've split this table into two halves. The top half is really the basics concepts that I want to cover in the first part of this talk, and that's concept of category, functor, and natural transformation. And the bottom half is what I'll try to get to in the second talk, and that's this notion of universal morphism, universal construction. So let's just focus on the top half of the table. There are two kinds of structure. You can think of two kinds of structure. The structure within a particular category, which includes some notion of object, some notion of arrow, and some notion of composition, which Britt had already introduced. And then you can, in the second cluster, the second row, there's also a notion of structure between categories. The category itself, a map between categories called the functor, and a map between functors called the natural transformation. And so one way to get a sort of an intuition as to what's going on here is by analogy to similar related concepts in, say, cognitive science, and in particular analogy theory itself. You can think of an object as some kind of entity, a map, an arrow as some kind of map between entities, Now, composition is sort of some sort of bivariate map, taking two things, in this case, two arrows, and producing an arrow. And so you have this natural sort of dimensionality here. And these symbols on the left-hand side sort of give you an intuition as to how these concepts relate. So if we think of an object as a dot, and an arrow as an arrow, and then a composition is a kind of this double arrow between arrows. Something analogous is happening also at the level of between categories. So you can think of a category also as this big dot, functor as an arrow between these dots, and again, natural transformation as an arrow between these functors. Now, and again, there's this notion of dimensionality here crops up, and this note and oops. And it's this concept of this square here, this called the commutative square, that sort of unifies all these various concepts, at least conceptually. Okay, so you think of this category as a kind of geometry of types, and this notion of dimensionality is happens at quite a few levels. So as I've already introduced, a category can be thought of as sort of like a zero-dimensional object, but keeping in mind that inside a category has its own internal, can have its own internal structure. We're going to align this concept with some notion of composition, or a basic notion of composition of cognitive science. And a functor is that sort of a one-dimensional concept, and we're going to align that with this notion of representation, and then natural transformation as a two-dimensional concept. And so all these three levels of concepts are all encapsulated in this single diagram. So what we have here is we start at the bottom. We have this object and arrow in some particular category, let's say called categories, and they get mapped to objects and arrows in another category. And the mapping is done by these functors we've seen. So what we have is, and how this notion of representation comes about, is that what a functor is doing is sending these objects and arrows to some image under a functor f, and this other second category functor is doing something similar. And so we can regard this functor f as a kind of representation of the original object and arrows. This functor g is another kind of representation. And then and from there we can think of the natural transformation as some sort of structurally consistent map between these two images. And so we have this notion of geometry, or dimensionality, 0, 1, and 2. And there's also an algebra underlying this. Okay, we have the arrows as a map from between objects. We have this notion of composition of arrows, and importantly, we have this notion of commutativity between in this square. So it's not just any square of arrows. What the commutativity is saying is that this map from this path, use the graph theory analogy, from here to here is the same as this path from here to here. We can say that they're equal. And so you can think of commutativity as analogous or generalized notion of commutativity that you're familiar with in elementary addition, i.e. X plus Y is equal to Y plus X. Well, this is analogous in the sense that the order of horizontal and vertical arrows, the application to the composition is the same, keeping in mind though that this horizontal arrow and this horizontal arrow, even though they're the same type, they're different arrows in themselves. For example, this arrow here and this arrow here are not necessarily the same, and likewise this vertical arrow and this vertical arrow are not necessarily the same. But that's the basic notion of commutativity or commutative square, and how it relates to your more familiar notion of commutativity in elementary arithmetic. Now, you said that category, functor, and natural transformation can be thought of in terms of dimensions 0, 1, and 2. Well, composition itself can also be thought this way. We have, and this diagram tries to capture this idea. As was briefly mentioned by previously, both the arrows within a category, functors are also arrows, and natural transformations themselves are arrows, and all of these compose. And in this case, and this diagram just shows you how this relationship between composition. So within a category, you have the composition sort of utility is captured by this vertical array of arrows. The composition of natural transformations, horizontal one, and the functor is also composed, but it's in the sort of outer plane direction here. So we have these three notions of compositionality. In fact, we have other notions of compositionality as well, but this is sort of the basic one. Okay, so, and now there are a couple of category theory has many concepts, and it's often sort of bewildering when you look at it from a sort of algebraic point of view. What's going on here? Well, the idea of this sort of geometrical perspective is a way of organizing how all these concepts relate to each other. And in a special case where one of these edges is the identity array, which you've already talked about, well, we can redraw this simply as a triangle. And this is where where the identity edge is just implicit in this diagram here, as this loop here. Okay, so because as Brett already introduced, every object in a category must have its own identity array. So often these arrows are just not shown on any diagram. The same principle applies. Okay, so instead of having this commutative square is really just a commutative triangle where the path from this direction is equal to the path from this direction. And call this a commutative triangle. And this gets us very close to this notion of universal mapping property or universal morphism that I'll talk in the next talk. Okay. This is just a lead up to this point. Okay, and then finally, we can yet another special case is where one of these edges of this square is in fact an isomorphism. And we heard Britt introduce the notion of isomorphism. That is, an arrow is an isomorphism if there exists an inverse arrow going the other direction, such that when you compose these two arrows, you get the identity here, and you compose it in the other direction, you get the identity here. This is isomorphism. Now, in this case here, what we see, we can yet another way to make use of these commuting squares is that going from this, so previously in the case of the natural transformation, we went from the top left-hand corner to the bottom right-hand corner in two possible ways. In this case here, we can go from the top right-hand corner to the bottom right-hand corner, also in two ways, either this way, or we can go around this way here because we have the inverse arrow. Okay. And if this is a commuting square, then we know that these two paths are equal. And this is important for the notion of recursion, which I probably won't get to in this talk. I think I've got way too many slides. But the idea is that often when we want to, in a recursive computation, what you really want to do is compute this relationship, this map from A to B. Now, if these are isomorphisms, what we can do is go this way. And what we're doing is deconstructing A into its components, then trying to compute it this way. And in a recursive situation, this one here may also not be directly computable, so you might have to decompose it again. Okay, and you keep doing this until you reach a terminating condition, which allows you to finally compute it directly. And this situation here is sort of one way of category theory addresses the notion of recursion. So computing the original rightmost arrow is the same as is done by pulling it apart and then going around there. That's the notion of recursion. Okay, and so this just gives you, this is just a sort of conceptual view of the basic concepts that I introduced in the first table from a sort of a geometrical perspective. And so now, with the remaining half of this talk, I just want to go through a bit more detail. The way that I'm going to introduce these notions, category, functor, and natural transformation, by correspondence to some familiar notions of composition, representation, and re-representation. Okay. For example, when we say compositionality, okay, in a basic sense, it just means putting two things together to form something. So in cognitive science, say in a classical notion of compositionality, we say a composite symbol is built up by constituent symbols and their relations. Okay, for example, notion of a red circle built from the concept of red, a symbol for red and a symbol for circle. And the important point is that where the relationship between these two constituents is given by their order. So, for example, red circle and circle red are not intended not to be the same because their orders are different. One of the motivations for this is the notion of persistence and productivity properties of cognition, which we'll talk about later. Well, in category theory, we have sort of a corresponding form, and that's the composite arrow built up from arrows, which Britain introduced via the composition operation. So, for example, G composed F is built from the arrow F and the arrow G. And again, the order is important. So, for example, F of G is not necessarily the same as G of F. And the idea is we can build up complex structure by compositions of arrows. Okay, so here is a definition. Brett introduced quite a few examples of categories. And so here, what we see is the actual formal definition. And there are several ways. When you read category theory, you'll realize that the concept of a category is introduced in several ways. But here I've introduced it this way for reasons that become important later. But you can see here that category consists of this notion of objects, notion of arrows, and notice that the index is 0 and 1, again, reflecting this notion that objects are sort of zero-dimensional things and arrows are one-dimensional. And this notion of composition. It also has these three additional things, this notion of domain, codomain, and identity. And these things here are what tell you how the objects and arrows are related. And as already introduced, okay, so often we would draw these as composition as from A to B, B to C, and therefore there must be this composite arrow here. And the composition here, again, shown by this double arrow, says the combination of these two, and there must be an arrow here. Now, the way of introducing this is also quite the issue of graph came up before. So you can think of this category as very similar to a graph, except that whereas in a graph you'd have, say a notion of edge, of set of edges, and say a set of vertices, a set of vertices, and a set of edges, and what's a map between the edges, and every edge has a source vertex. It's given by the map there, and every edge has a target vertex, and it'll be just this quadruple here. But notice the difference here is that there is no identity and no composition. And so the question that came up previously was, well, what's the relationship between category? Well, when you see it in this sort of algebraic form, you can see quite clearly that a graph is like a general, it doesn't have this additional structure. This doesn't necessarily have this additional structure of identity and composition. So it's another way of looking at the notion of category. Okay, so let's do some examples. An ordered set is a category. So say, for example, we have three people, Anne, Ben, and Kaz, and we say that Anne is shorter, or not taller than Ben, and Ben is not taller than Kaz, and then so we have this arrow here, which we may write as less than or equal to arrow. And we have this arrow here, which we write like this. And therefore, by transitivity, as someone mentioned earlier, orders are transitive. That means if we have this arrow here, this order relationship here, and this order relationship here, then we also have this order relationship here. So an ordered set is a simple example of a category. And the point about this one is that in an ordered set, there's only at most one arrow. But as we saw previously, as we saw in the, and heard before, that in general, categories can have more than one arrow. And here's another example. This is the monoid that was introduced. So a natural number is a monoid. Sorry, the set of natural numbers with addition and zero is called the monoid. And this is classic one object category. And I've written it this way. So just to show you the correspondence between ordinary addition and the identity, for example, as shown here. But notice here that this star, the identity of this object is not important, but we just give it as a star. But if you were to just write it this way, then we see that there's an arrow here, a loop, corresponding to 1, and there's an arrow here corresponding to 2, and therefore, and what's happening here is the addition corresponds to a composition operation here, so 1 plus 2 means that there must be an arrow here, 3. And the identity is just the 0 arrow here. This is called the monoid, and every monoid is a one object category. Okay, and so introduces the net. And then the sort of the prototypical example of a set, and why a lot of this notation comes from sets. Sets and functions is the category of sets and functions, where the objects are sets and the arrows are functions, and composition functions. So in this case, where in the previous example, the arrows and objects are very simple, had no internal structure. In this particular case, the object is a set which has elements inside it. So we might have a set A, and then we might have another object, set B, like this, and then the arrow between here is just a function. And what it's doing, so there's structure at 2 levels. There's the relationship between the sets, and then there's the mapping of the elements between the elements. And it's for this reason why you see 2 types of notation here. A notation for the morphism itself, i.e. this arrow, and then for objects that have their own internal structure, like a set-like structure, then you'll have this maps to arrow to say what's happening on the objects. And so in this case, and composition is simply composition function. And you can see here, for example, if I have another arrow here from B to another object C, then we have this composition here, and it just and the reason for this sort of reverse notation is it just follows the composition of function composition. So, for example, F applied to G applied to F is just the same as saying G of F of A in this situation. Okay, so there's some basic examples. What we want to do now is to, and I said as a theory of structure. So what we want to do now is to look at structures as a kind of object. For example, the monoid that I introduced before can be re-expressed as a set M, and this multiplication operation. So, for example, in the case of addition, the multiplication operation is just simply elementary addition. And another map which picks out the unit. So, for example, picking out the element 0. So, for example, down the bottom here, multiplication is just actually elementary addition, and the unit is the number 0. And so, by doing it this way, we can re-express the monoid as 2 arrows. This multiplication arrow from the all pairs of elements in the monoid, and this arrow here that picks out the unit. And then once we do that, we combine this into a single arrow in this way. And this has advantages when we want to move from when we want to move from just the structure within a category to the structure between categories, and as a way of motivating. I'll skip this. Similarly, you can do the same thing for a category. In fact, as we said, a monoid is a very simple category, which has just one object, but category generally can have many objects and has this additional structure. And you can do the same sort of thing, re-express the category as this collection of arrows and then put them all together as a single arrow. And in doing that, that leads to a notion of naturally to the notion of functor. Okay, and to do that, how we do that is make this move from going from arrows to arrows as objects. So here, for example, we have an object. Here we have an arrow going from between 2 objects. And what we can do as we move up between these levels, we can treat this arrow as an object in its own right. And if we have another arrow, which we treat as an object in its own right, then the map between these 2 objects is a pair of arrows such that these two, this square of arrows commutes. And so we're sort of moving up a level now. And the composition now is just the pasting of these squares. So if we have, the squares are now the arrows. So we have one square here composed with another square here, and that gives us this outer square. Okay, and so we have this notion of composition at this next level. Okay, and so when we do this, okay, so here's our monoid expressed as an arrow. So the structure of monoid expressed as a single arrow. So now we have our monoid now has become an object. So previously we said a monoid could be a category. Well, now we're treating it as an object. And we have another monoid here. And then so the map between monoids is just a map between the corresponding arrows, i.e. this commuting square. And so here we give that we have the definition of a monoid homomorphism expressed as a commuting square. And so it captures this notion of the commuting square as quite a sort of unifying concept of it. And you can compare this definition here with the more algebraic version of the definition here. So a lot of these slides have a lot of technical detail, which I'm going to skip over in order to get through the talk on time. So I won't explain all of it. So if you're interested, you can ask me questions later, or you can just go through the video, the recording at your own pace at a later time. And so you often wonder why, in mathematics or category theory, why we have where these definitions come from, and this sort of notion of commuting square sort of sheds light on this. And so, in fact, we've already, since a monoid is a category, a monoid homomorphism, therefore, is a map between categories. It's a special case of a functor. Okay, so we're going to align functor with this notion of representation. And in the classical version, a representation, so a basic understanding of representation is where one thing stands in for another. So the classical version is this notion of semantic relations between parts mirrored by their syntactic relations between corresponding symbols. Okay, so for example, square is left of, a circle is left of square, you might have some sort of symbol for the relation left of, and some sort of symbol for circle and some sort of symbol square, such that the order between the syntactic representations mirrors the semantic ones. And motivation for that, a motivation for that is the notion of systemicity representation. Well, the functor can also be sort of regarded analogously as a kind of representation. So we saw the functor, what it does is map. It's a mapping such that the mapping on the component arrows equals the mapping of the composite arrow. It's analogous to what's on there. And so in diagrams, it would look like this. So here we have a bunch of objects and arrows in one category C, and then another bunch of objects and arrows in another category D. And the idea is that the mapping between here, and again, this notion of square is preserved. So the mapping of the functor maps the objects and arrows in a way that it preserves this compositionality. And it also preserves the identities. In fact, it preserves three things. It preserves the domains and codomains of the arrows. There's the domain. This one is mapped to here. The codomain of this arrow is mapped to here. And so the arrow here is mapped to here. Okay, so it preserves the domains and codomains. It also preserves identities, which are not shown in this diagram, and it also preserves composition. So the composite here is mapped to the composite over here. Okay, and again, like we did with the monoid, we can re-express this as another commuting square. So the idea of preserving domains is captured by this notion of these two arrows here getting mapped from this category C to this category D. So here we're re-expressing the functor as really two maps: a map of objects, okay, F0, and a map of arrows, but not, it's just any map, it's a map, and we can express it, again, we can express this relationship by these commuting squares. Okay, so, and again, notice that this is closely related to the idea of a graph homomorphism. And a graph homomorphism, remember we said that these C1s correspond to the edges and the C0 with the vertices in one graph, and you do the same thing on the other graph, and the domain map and the corresponds to the source, and the codomain map to the target. Well, in a graph homomorphism is very simply just this relationship. However, graphs are required to have identities in composition. So very quickly, you can see the difference between, say, graphs and categories by the fact that the categories have this additional structure that must be preserved by the functor, the structure on the identities and the structure on compositions expressed this way. And so, again, the advantage of doing this sort of geometrical perspective. And you can make this, you can express this even more in the same way as we did for the monoid. Okay, a single arrow expressing the structure of a category. And again, the functor, all it's doing is just is another kind of map between the two structure arrows. And so in this sense, I meant that category theory is a kind of theory of structure, and that it treats structure as a kind of as an arrow, some kind of typed arrow between entities. And this square here really captures this more traditional, the more algebraic notion of functor. Okay, so that gives you some intuition as to how all these things hang together. Okay, so what we see is that we can go from, as we go up the levels, so instead of talking about within a category, we talk between categories. What we're really doing is we're converting arrows into objects, and then we're mapping between these objects. And it's a bit analogous to the notion of treating a verb as a noun or an action as a state, and so on and so forth. Okay, and so finally we come to the notion of natural transformation and how we're going to how this corresponds to re-representation or transformation of representation. So we can think in the classical version, say we might think of cognitive process as some sort of symbolic manipulation, symbolic representations and processes that manipulate those symbols. We can think of natural transformation sort of analogously. If we're thinking of a functor as a representation, then a natural transformation is a map between these representations. Again, here we have that diagram I showed you in the beginning. Okay, and so a natural transformation is actually just a family of these arrows, as I introduced here and here, such that they're not just any bunch of arrows, but such that this square, again, we have this notion of commuting square. Okay, so you go from here to here to here. These two things are equal. Okay. That's the basic concept of natural transformation. And again, this sort of common theme of this commuting square underlies all these concepts. It's sort of a way of sort of orienting your thinking to how what all these concepts and category theory are about. Now we'll finish up with a couple of quick examples. So re-representation, one sort of simple example is the notion of approximation. So the ceiling function, for example, sends each real number to the smallest integer, not each real number x to the smallest integer, not less than x. Okay, we can think of this situation as a kind of natural transformation. And so the way this is a very simple example, but the way this is happening, what's happening here is that here is our original numbers and their order relationship, okay, in the original category. Now, a very simple functor is just the identity functor. What it does is just move this thing here, and the image of this functor is just the same as the original thing. Now, the ceiling there is both a ceiling functor and a ceiling natural transformation. So all the ceiling functor is doing is sending each object here, each number to its ceiling. So, for example, a number 2.1, 2, 3, and its order relationship. For example, the order relationship between 2.9 and 3.1 gets sent to 3 is less than 4. Okay, so that would be sent there. So this is in the category of reals. Here we're working with integers, and then because the important thing about functors, natural transformation is that they're between two functors with the same domain and the same codomain. Although the codomain and the codomain may be different, but they have to be the same for each functor. And therefore, we have to inject this in here to get back to the real. This is a very simple example of this notion of what we're doing is sort of re-representing these numbers from their real form to an approximation, i.e. an integer form. Okay, and here's another example, sort of a relationship between parts and wholes. And this is called a projection. And the basic idea here is that the relationship between, say, A and B and its constituent A or its constituent B is also another kind of natural transformation. And notice someone mentioned in the previous session about the relationship between logic. This is quite a general construction, and the actual what's actually happening will depend on the particular category. But you can see the analogy here between the notion of whole and part, and also the notion of logic. For example, compare this notion of taking this whole, this A and B, and pulling out its part is analogous to the notion of having A and B implying A. And this is actually a formal, not just a conceptual, but also a formal analog situation. This is another example of natural transformation that is quite useful. And finally, to finish up, I mentioned earlier that the special case of a square where we have the identity map here. In this case, we have a special kind of natural transformation where instead of having the square, we have the triangle, commuting triangle. Recall here that X here has an identity arrow on this thing. And so what's happening here is this is a natural transformation between what's called a constant functor, which is sending all these objects and all these arrows just to the one object, X, and its identity more arrow here, and some other functor, G. Okay. The reason why this is useful is that it's very close to the notion of universal-morphism that I'll talk about in the next talk. Okay. A very simple example of this is in the example with the natural numbers. 0 is the least natural number, and you can express this as a kind of natural transformation in the sense that there is a functor sending all the natural numbers to 0, that's here, and just the identity functor, preserving all natural. Now, what it's saying here is that it's the least, 0 is the least number, so that every number here is less than or equal to 0. And this is another very simple example of a natural transformation. And the reason for introducing this is that once we get to here, we're very close to this notion of universal morphism. So that it covers the sort of basic concepts of category functor natural transformations, which we use for this notion of universal morphism and its application to systematicity that I'll talk in the next talk. Okay, so I'll finish there.
This is Brett speaking from the room. Did you want to take a moment for questions before going on to part 3?
I'll take a break. Yeah, so if you want to ask questions, let's like a couple of minutes break before going on to the final.
All right, so we'll have a couple minutes of leg stretching and questions. Anybody in the room? Yes, Alexander.
Yes,
If you sort of kind of yell at the mic that's next to you there. You don't have to stand up.
The example with the order made me think the word arrow, there are lots and lots and lots of little arrows. So the relation that 3 is greater than 2 is one arrow, and another that 5 is greater than 4 is yet another. Is there a concept of what in algebra is called the order, which is an entire collection of arrows binding many numbers in a systematic way? So I think you called it a function at some point, but is there a notion that these arrows form chains somehow and so forth? So when you talk about composition, there is this notion that the arrows hook up with each other, but somehow something seems missing and it seems important. Does the question make sense, or?
Yeah, so in those very simple examples, the objects were just individual elements, but you can have, like in the case of a function, a set of elements, for example. And so an arrow can be doesn't have to be just so little, so small as you put it. And in fact, the natural transformation is an example of that situation. I'll just try and get back to it. I'll just try and get back to my, oh, sorry.
Did you have a take on this as well?
Example in,
So so the question was about orders, and I think so the greater than less than is an order, but any category in which each of the objects are connected by no more than one arrow gives you some sort of an ordering. Doesn't just have to be limited to natural numbers and greater than or less than. So the categorical treatment of of an order is in some ways broader or more inclusive than just the greater than relation is like one. So you have a category of all orders in which this is just one, could be one object in the category of ordered collections.
yeah, so in this example here, the natural transformation, recall that there's just a single natural transformation here, a single arrow, but inside this arrow, it's really a collection of all the little arrows. Okay,
yeah.
The natural transformation is a family of arrows. So this natural transformation, the single arrow here, is really encapsulating a whole bunch of arrows.
So that should help them understand why this was sometimes originally called abstract nonsense, right? Because it's just, we have this big abstraction that we can build, but it's, yeah. So I don't know. So maybe we can talk more about that later too, Alexander. How about, are there other questions from the online community that wanted to get clarified with Steve on these background concepts before he goes into the more detailed use of them? How about in the room here? People who want to get him to clarify a point before he presses on? Yes.
I'm still trying to understand the difference between a functor and a natural transformation. It seems like because of the identity functor, they're always equivalent, like they can always be equivalent. And am I understanding that right?
So the question, Steve, from the room is distinguishing functors from natural transformations.
Mhm.
And the sort of second half of that question is whether it's the case that there always are natural transformations between functors.
I know that they're not always natural transformations between functors. And the example I gave, the two examples I gave were very simple. So in general, the natural transformation is sort of a relation between if you think of a category as an entity and a functor as a relationship between two entities, then the natural transformation is like a second order relationship, a relationship between relations. It's just that the simple examples that I gave, it's a bit like an analogous way of thinking about it is like the relationship between vector and matrix. So you can have a matrix as sort of this square of data, and you have a vector, it's just a string of data. Well, you can think of a vector as sort of a special, is equivalent to a special, one column matrix, but they're really two different types. Okay, but there is an equivalence between the two. So in the very simple example that I gave of natural transformation, you can think of it as a very simple. You can see the functor as being equivalent to a very simple case of a natural transformation, but the two concepts are not equivalent, just like concept of vector and matrix are not equivalent.
The examples that come up often have the examples often use two functors that have a natural transformation between them, because those are often the ones that make the teaching point easiest, but in fact it's not the case. And so that's a natural transformation between two functors is sort of a special thing that's worth taking note of, which is why they're used so much as examples. Okay, so we have so you're good to go until noon, Steve, for part two.
Okay.
Oh, wait, so Jeff wanted to add something from within the room?
I don't know if this helps or not, but you're talking about, functors and natural transformations. And one way to think about what I mentioned before, like a functor is a representation of sort of one category within another category. And so if I might have two different functors between two categories. So one way of representing object morphisms in one category and in another one, and a different way of representing the object's morphisms in that category. And a natural transformation is where to compare those two different representations. So the functor itself is a representation of the data. A natural transformation is a way to compare those two different representations. I don't know if that helps at all, but that's one way to think about it too, the difference between them.
Okay, Steve?
Okay, and thank you very much for that. So now we want to move on to this notion of universal morphism and its relationship to compositionality. And I think since I used up so much time in the first talk, there's a lot of slides here. I'll skip most of it if you're interested and look at them later. One of the difficulties of category theory is that you need to build up quite a few concepts before to get to the ones that you're particularly maybe interested in. This notion of universal construction or universal mapping property, it's fairly, although it's technical, it's fairly intuitive. So for an intuition, just suppose, for example, traveling to the conference, you can think of, suppose you come from, I don't know, overseas, you're coming to this conference. You might come from, say, Tokyo, or you might come from, say, Paris, or any other city. And to get to the conference here, for example, if you're coming from overseas in particular, probably the first thing you have to do is really get to the airport, like Toronto, whatever. Let's say this is one airport in Toronto. Okay. So everyone, almost all the delegates, to get from wherever they came from to the conference, presumably we'll all have had to do the same thing. And that is, had to arrive at the airport first, and then take let's say the train from the airport to the conference center. Okay, and this is sort of a basic notion of universal mapping, in that there is every one of these red maps, morphisms, is composed of a common map here, which is this one here. Okay, it's a common element called the mediating morphism, and some unique morphism that picks out the individual, that identifies individual root. Okay. Here and here. Okay. And so the idea of a unimap, if you have some sort of universal situation, universal map, all of these maps, what we said, I think as Toby mentioned earlier, factor through this common map here. Now, if you get to the conference, everyone who came from overseas had to get, let's say, for argument's sake, for illustration's purposes, have to take the train from the airport to the conference center. And that's called the mediating map. That's the basic. So conceptually, it's quite a simple idea. Now, formally, it looks like this. I think I'll just walk through this and see how we go. So there are two forms, what's called the primal and dual form. The one I just showed you is more the dual form, so you can do that way, but it doesn't matter. It's a little bit technical, actually. So what it says is that the universal morphism, so you have some starting point X, it's object X, okay, which is here. And what we're saying is we want to go to some functor F. This is the functor from here to here. So conceptually what's going on is that this functor is going from some category A to some category B where X is in. And what the universal morphism is this pair. This pair A alpha, which consists of the object in the category A, and its morphism alpha. And conceptually what's going on is that if our object X is here, and we have all these things in here getting mapped into all these things here, then the universal morphism is essentially the closest point you can get to X from this particular point, from a point, okay. So this point gets mapped to here. Okay. Or to go back to the airport analogy, going in the other direction, B to here is our common arrow. So in this top example, in the primal form, the alpha is the common arrow. It's common to all these other arrows here. And what it says is that universe is this object A in the original category and this arrow in the other category, such that for every object Y in the original category and every morphism G, we can factor through this common morphism here, a bit like the airport analogy. Okay. And it factors through uniquely. Okay. So for every object Y and every object G, there is this unique dashed arrow U, such that, and now here's where the commutativity condition comes in again, such that these things here commute. In other words, every one of these things is composed, every morphism here is composed of this common morphism here. So a very simple example of this situation, again, going back to the ceiling function, is that the ceiling of X is the smallest integer, not less than it. Okay, so for example, the ceiling of 2.1, so here's our 2.1, is 3, and 3 is the closest we can get to 2.1 from the category of integers to category of reals. Okay, so we have all our numbers here. 3 sits here, and we have to map all these across. Okay, and the closest point we can get to 2.1. So in the case that we're using just an ordered set, this literally is the closest. Okay. So that's the basic intuition. But this concept is quite general, okay, and applies to a whole variety of situations. In particular, until now, previously when we talked about composition, we've just talked about composition of arrows. Okay, so an arrow composed with another arrow to produce an arrow. But also we may want to talk about composition of more general situations like composition of objects. And a very simple case of this is the composition of two objects. For example, composition of object A and object B is called their product. And this situation, and not only is product, but it also has two maps that retrieve each of the constituents A from the composite constituent A from the composite A cross B and constituent B from cross B. And the limit is a way of doing this. And the limit is a special case of a general class of universal morphisms. And a way of doing, and yet another way of thinking about compositionality, in this case, in this very simple case, composition of two objects. Now, precisely what that means will depend on what category you're working in. And how this works, how this relates to universal morphism, is a bit, it requires a few steps to understand, and that's the purpose of this table here. But what I'm just going to do is give you some intuition as to what's going on in terms of, by way of thinking about attention. So, for example, let's talk about the product of objects A and B. You can think of A and B as let's say we have some sort of field of view, and we want to pick out two objects in that field of view, A and B. And we can think of that what's going on as a kind of spotlight of attention. So suppose, for example, we're here, and what we want to do is pick out these two objects. And this is called a cone. It has a vertical vertex here. What I should have done is actually introduced the mesh product before, but I didn't do, so let me just back up. No, it doesn't. What we want to do is to we want to get view both A and B. And what the product is, what the limit is doing is giving the best possible view of A and B. So you can think of, there are many ways to view A and B, many cones that consist of a sort of starting point object Z and a sort of a base here, the thing that you're looking at, targeting the contents of attention. And this cone is sort of the spotlight on this thing. And then you can have another point of view. Let's call this Z dash. And say another spotlight of attention. And what you're doing is shifting your perspective from here to here. So this blue arrangement here is called a cone. This red arrangement is called another cone. And this map between these two cones is called a cone, and the morphism is map of cones. You can think, conceptually, you can think of what's going on is you're picking out two objects, and the limit, or the best possible way to pick out these two objects is called the limit, or the universal cone. And the vertex of that universal cone will be the product of those two objects. And that is called the limit. Okay. And so limit, and this in this very simple situation, we're just picking out two objects. And so what we call the shape of attention, or the window of attention, is just these two nondescript objects that are used to identify or pick out or index two particular objects, A and B. And the limit is the best possible way of viewing A and B. And that happens to be, and that turns out to be what's called its product. It turns out that this situation, there are many, now you can do this in a whole bunch of ways depending on what shape of attention that we want. So I just used this example where the shape of attention is just two objects, but we can have, for example, we can pick out just a single object, or we can pick out an arrow instead of an object, and so on and so forth. Britt mentioned the notion of an empty category which has no objects, and in this particular case, the shape is empty. Now, this is also important. And all these cases, they all have the same form, and from this you can compose objects and arrows in a whole variety of ways beyond just simply composing two arrows to form another arrow. Okay, so this just reiterates the same idea. So in the particular example that I used, we would have A and B as what's called the base. That's what we're looking for. And then we have one cone here, picking out this base here. And we have another cone doing the same sort of thing, but picking it out from a different perspective. And then we have a map between these two cones. And the universal, the limit is a kind of, we can reorganize this diagram by, instead of looking at the individual objects and morphisms within the base of the diagram, I think the contents, we can just put them all together just as a single, I represent this as a single thing here. And so that the limit is, as you can see, has the very same picture as we saw for the universal morphism, i.e. the limit is this object here, and this common arrow here. In this case, it's a cone, such that every other cone factors through this. So, for example, this cone here, also pointing to the same diagram, factors through the limit in this way. And in our particular example, so what we're doing is we're trying to recover the pair of objects A and B from their composite A cross B. And that's what this is doing. And it's somewhat technical, but this shows you how to formalize this notion of commonality amongst a bunch of things. Okay, that's what I said in the previous slide. Okay, now that was the general definition of a particular limit, in this case, a product. Now, the specific example will depend on what category you're working in. If, say, for example, we're working in the category of sets and functions. In this particular case, the product let's say working in sets. The product will be just a Cartesian product of sets. So we have a bunch of, let's say we'll just draw it as a bunch of pairs of objects, A, B, A, B dash, so on and so on, A dash, B, so on and so on. So that's our product. Here, that's the product object. But remember that there are two parts to a universal morphism: the object and the morphism itself, the two projections. And we can project that out. We can project out the A, the A dash. Okay, so this is in the set A. This is called the projection. And we can also project out the other component, B dash, okay, etc. Okay. Now that's the product in the category of sets and functions. However, if we're working in a closely related category, the category of sets and inclusions, where we just have sets and subset relationships, then the product is a little bit different. The product is more familiar as the intersection. Okay. So in this case, A times B. So you often see in category theory, the product will be written as A times B. What that actually means, what that specifically means depends on what category you're working in. So in this case, in this particular category, the product of two sets is just the intersection. Okay. And so we can see this more intuitively as bit here. And this bit here. So here is our A cross B, but now which is actually just the intersection. Here is A, here is B. And the projections now are just the insertions of these elements. This set here, this set here. Okay. So have a, and this is how we were talking about before about the notion of how one construction in one setting is maybe closely related to another construction in another setting. You can see this has the same form. Okay, it has an object and two maps picking out the constituents, and just as this one has an object. But the details of these constructions differ because of we're working in a different category. And so that's a very basic notion of composition of these two sets into this set, depending on what category you're working in. Okay, I think I'm going to just go through this quite quickly now so that we can finish on time. Another example of this is the terminal object. Okay, again, has the beauty of limits, that they all have the same general structure. but they just vary by two things. One, the shape of the category that you're working with. So in the previous example, the shape was a pair of objects. And in this case, the shape is actually the empty category. And I won't go through the reasons for all this, but in this case, we have what's called a terminal object. And that means that every object in the category points to, or ultimately ends up, this object here. This is called the terminal. So if we have another object here, then there'd also be a map that goes into here, and so on and so forth. Okay. But the whole setup is exactly the same. And then, of course, as with the product, the specific terminal object will depend on what category you're working with. So, for example, if we're working in the category of sets and functions, the specific terminal object, it will be any singleton set. And the unique map there is the constant function, sending every element to the same one element here. However, say, for example, we're working in the category of ordered sets, then the terminal object will be the top element. Now, the beauty of another nice aspect of category theory is if you have a particular construction. We saw several slides ago that there are two forms of universal morphism: a primal form and a dual form. And the dual form is the definition of the dual form is really obtained by reversing the directions of the arrows for the definition for the primal form. So we talked about limit. We can also do the same thing here for co-limit, in which case the arrows go in the opposite direction. The same thing, same basic principle is worked through, but in the case of the co-limit, because the arrows are in a different direction, in set we have what's called the disjoint union as the co-limit of two, and yet another way of composing two objects. And in the case of sets and inclusions, then the co-product is the union. Again, and many category theory constructions have these two forms: this primal form and this dual form. And so we can come up with many ways of doing compositionality just from this very simple notion of limit, or its dual form co-limit. Now, how this relates to systematicity, I'll just do, so that we have enough time for questions, I'll just do a 5-minute run through. The basic idea of systematicity was that cognitive abilities just are not just randomly distributed, they are organized in certain clusters of cognitive abilities. Right? So the sort of archetypal example, if you can understand the expression, if you're a native speaker of English and you can understand the expression of John loves Mary, then you can also understand the expression of Mary loves John. Or conversely, if you can't understand that John loves Mary expression, then you can't understand. So it's a kind of equivalence class over cognitive capacities. Now, the classical notion of this is to think of the sort of language of thought idea is that all these capacities have some sort of common underlying grammar, and that each capacity then is instantiated by a specific instance of this grammar. However, there are issues with this particular explanation, and if you're interested in this notion, then Ken Aizawa's book goes through this in great detail. I won't go through all the details of this, but I just want to show you how the systematicity property relates to the concept of universal morphism that I just introduced. You can think of, and I'll do this very intuitively just to get through the slide. You think of these. So the idea is we have these sort of clusters of capacities that you can do, which I'll just level. The idea is that either you have all of these or you have none of them. Okay, there's no in between. Okay. So now how this relates to universal morphism, as we've already alluded to in the earlier slides. And the idea is that the universal morphism is capturing some sort of common element of this cluster. So if we think of these cognitive capacities as some kind of arrow, then we can think of the some sort of prototypical or schematic or component, and that all of these capacities share, and then compose with that and some unique arrow picking up the individual capacities. Okay. The basic idea is that if you, in this way, if we say that these arrows now are being interpreted as some sort of cognitive capacity, for example, some ability to represent some situation. So what we're saying is that all of these cases, in the category theory sense, factor through this common arrow, this mediator here. And so in this case, if you were to disrupt this arrow here, cut this arrow here, then you would effectively cut or remove all of these abilities. And so this mediating arrow essentially picks out an equivalence class of cognitive capacities. And that's sort of the conceptual intuition behind this notion of systematicity as followed from as a universal morphism. This is a specific example, as you might do in a psychological experiment, for example. Colored shapes composed of two features, a color feature and a shape feature. And so in set, you could model this as a product of a set of color features and a set of shape features. And then it's just the Cartesian product of this would give you all pairwise combinations, as I think I showed in the previous slide. And then you can use this as a way to test, well, to what extent are people really that systematic? And then set up this. So here, previously I just talked about the product of two objects, say A and B. You can also have the product of two arrows. So in a sort of an experimental setup, you have say a set of cues and a set of targets, and the task would be to learn this map from cues to targets. But the way we've set it up is actually this map is really the product of two maps, a product of this map F and a product of this map G. Okay. And then the idea the intuition here is that let's say we have our product of cues and being mapped to this product of targets. There's a whole bunch of these in here, and a whole bunch here. Now, if you can do, and we would have some sort of training set so that you can do some of these, and the question is, if you represent these cues and targets as a product of the constituent cues and targets, then you would expect to be able to generalize to the remaining examples. You can think of this as the notion of systematicity. So this situation here generalizes or extends the situation here of the entire set. Okay, so I think I will just, and the idea here is that you can run an experiment to test this situation and to what extent people do in fact do this this kind of systematic behavior. An example of this is done in this paper here. Now, one important feature of it seems, so from the examples I've given so far, it seems very much like the notion of product in category theory is very similar to the notion of sort of classical notion of product, where you have this idea that if the complex representation is actually just a composition of its constituent representations in some way. And it's called the tokening principle. So that is, whenever you have the complex representation, you also have its constituents. But in category theory, there are many possible products. But so the one I just showed is just what's called the canonical version. But you can have other situations. For example, all the elements can be relabeled just as the numbers from 1 to the number of elements in A times the number of elements in B. The critical thing here is, for this to be a product, you need not just, so it's not just the set that's important, but it's the maps that retrieve the elements in this case. So for example, instead of having, so for example, in the classical notion, you might have, say, A. In the classical notion, you would have, say, A, B as a pair, and then you'd retrieve A, and you retrieve B by just the simple projection maps. But in category theory, for example, you can just have the number 1, as long as you have the appropriate map here, such that 1 maps to A, and then 1 maps to B. And then for 2, for example, let's say 2 maps to that one, and then 2 maps to B dash, and so forth. But in fact, it's not necessary to have a symbol. The sort of symbolic representation is not really necessary in the category theory view. Category theory offers a sort of more general notion of compositionality than the classical view. Or you can think of the classical view as sort of a special case. So that's the so-called canonical product. But and the thing about products and limits generally is that I'll skip it. Is that these universal constructions, these products or limits generally, are only unique up to what's called unique isomorphism. It's not just that they're unique up to isomorphism, but there is just one. For example, we can switch the order of the individual constituents A and B to be B cross A, so long as we have the appropriate switching in the 2 morphisms that retrieve the constituents. Then this is a product. But this is also a product. They're isomorphic, but not only are they isomorphic, there's just one and only one map going between the 2. And that's why in category theory, it'll often state that it's the product. But what they really mean is it's just a product, and but this relationship holds. And this relationship holds that all products, all limits, or co-limits, all unique, or universal morphisms in general. And so we have this different, sort of more general notion of compositionality that is afforded by sort of the classical notion, where you don't need to have this tokening principle. Okay, so I'm almost finished, I think. I had many more slides, and many more things to think about this, but this is sort of a very basic conception of how the relationship between systematicity property in cognition and the notion of universal morphism category theory as a kind of, in particular, product as a kind of limit and its relationship to compositionality. There are many other kinds of universal constructions. Another one that, which can be also related to other aspects of cognition, which I won't go through. I just want to finish now with the last couple of slides. Just to give you an overview, I said category theory has a sort of geometry of squares. And the idea was that when you first get into category theory, you see there are many definitions, many examples, many sort of small and large theorems. It's often hard to find your way around the theory, but one way of thinking about this, one way of sort of orienting yourself is this notion of commutative squares, sort of a recurring theme throughout all the examples that I gave, although I didn't give lots of details. But the idea is, for example, we saw for example, in the notion of a natural transformation is this notion of parallel arrows. Okay, so we had the key point, sort of the unifying concept is this sort of square of relationships between entities. Okay, but we can use this square in a variety of ways. For example, we can use it to, as Jeff already mentioned, as a way of translating or transforming something, a representation on the left-hand side to being a representation on the right-hand side. Hence this sort of symbol that I used here to indicate that. If we had more time, these natural transformations can be re-expressed in terms of more general construction called a common category. And conceptually, it's very similar, except the orientation of the square is different, and also the typing of the square is different as well. Yeah, that's why it's not only just the geometrical aspect of this thing crucial, but also the underlying typing that's going on. I didn't talk about the recursion and co-recursion because there's not enough time, but again, you can think of this analogously. That's one way of doing it, as a way of transforming things. Another way of thinking about it is that it's a square of relations. So we have this notion of consistency or alternative paths. So the simple case was going from the top hand. And so the reason for this is sometimes you may want to go this path because it's easier, or you may want to go this path. And so often what you do is re-express one composition of arrows as another composition arrow, perhaps because it's computationally more easy to work with. And in fact, I alluded to that in the introduction. For example, when you do recursion, for example, what you want to do is compute this arrow here, but you can't do that directly. You have to do that via a detour. Okay. So that's another way in which the square, this notion of commutative square, comes up as a notion of alternative path. And then the notion of universal morphism as a sort of special, a very important special case of this is a kind of grounding of the square where we start at sort of a point here and we progress from points to arrows, or we can go in the other direction as well. So it's like a termination here. So what we're doing is transforming this arrow into this point here, and this is a way to talk about the relationship between different levels. And this is all built on, and we talked about, there are other ways of doing this as well, which I didn't talk about in great detail, but the other
Steve, do you want to allow any time for questions? Because I think we're running close to some people's breaks here, and just if we want to give them a chance to ask you anything, we probably ought to do so.
Okay, so I'll finish here. Just the final point that we can use this principle in a variety of ways in cognition, and there's just some examples. And then, if you're interested in, there are many introductions to category theory, and this just shows you some of the ones that have already been mentioned. For example, the applied category theory books, the conceptual introduction, and more formal and computational philosophical introductions as well. I'll finish there. Thank you.
Okay. Thank you. So
there is an online question.
Yeah, I was just going to say, so if people wanted to take a more leisurely tour through this, the 2010 article is the one where you sort of lay out the theoretical rationale, and then your 2016 article is the one where you use it to motivate an empirical test of the categorical ideas.
Yeah, that's right.
And then the 2021 one is a sort of another overview of category theory that's kind of a summary of a lot of the things we talked about. So that would be the guide to people wanting to get more detail. Okay, and the online question?
There is an online question from Zachary Dubak. Do you have any thoughts about how the brain implements systematicity in light of these ideas?
Okay.
We're starting at 1:30 for people in the room. If you want to.
A very good question. I talked about this in a sort of a more general context. More general construction, but you can think of, for example, the relationship between prefrontal cortex and say and parietal cortex as one area representing the schema, the common part, and the other area representing the instances that get mapped between them. So there's a long story that I would like to talk about in this, and so if this person would like to if people want to hang around, I'll hang around and ask them, answer these questions in more detail. Yeah. The short answer is yes. I think there are ways of thinking about this in terms of the underlying brain architecture as well. And this distinction between schema and instance it would be one way to think about this difference.
Other online questions you got there for us?
Not for now.
Okay, in the room, people want to, okay, we got one in Salvador, right? Yep. If it'll save me from having to repeat the question. Yeah.
Can you hear me like this?
Yeah. So
Not
we're
quite.
getting, he's getting to the mic, Steve. Just get a second.
Hi, so you gave a wonderfully intuitive explanation of how the theory can help us operationalize and sort of understand and see systematicity in terms of the, what did you call it? Mediating arrow. I wonder if you could do something similarly intuitive to help me understand, have some notion, intuitive notion of how the theory then formalizes, operationalizes the notion of the dependency between the specific arrows within a set of systematicity equivalent class of cognitive functions.
Oh, so if you have two such arrangements, or for example, go back to the previous slide. Sorry, I can't, the product example, sorry, there's a lot of slides to flip through, but the product example where there was a product of cues and a product of targets would be one example. Sorry, on the sorry, I can't get taking too long to get the slide that I want, but the product of cues is an example where the two kinds of systematicity. Here we are. This one here. So here we have the product here. Here we have another product here, and these are related by this product arrow. And so you can think of this as as picking out this bunch here. So this picking out this bunch here, and so that's kind of a translation here. I'm sorry, that's not a very good explanation, but it's the same general idea. And so we can think of this arrangement. So here is our meeting out arrow. Here is our meeting out. Here's a transformation of these meeting out arrows in such a way that it preserves the this kind of relationship here.
All right. Other question from folks in the room? All right. Do we have more from anybody online at this point? I can't see the display.
No,
Okay, so thank you again, Steve, and thank you for staying up so late. It is now, I guess, 1 a.m. Where he is. So we are going to come back for anyone still online at 1:30. We will resume the afternoon sessions with 2 talks from Toby and 1 from Jeff. So thanks.
I'll hang around for a while. If people want to ask questions in the chat, I can just do it here.
Okay, so Steve is hanging around for a little bit for questions in the chat.